Okay, so welcome everyone. So today we're gonna switch topics from sequential decision making that we were looking at for the past 3 sessions to back to deep learning. So before we get into the subject matter, let me quickly discuss some logistics. So let me share my screen. Okay, so we are here actually. So assignment 4 was due yesterday. So basically, it was a couple of questions on bandits and a question on just working with DQN. Of course, Cardpool is one environment in the OpenAI Gym package, or and you could have also used something else later on if you want to try. And DQN is not the only algorithm, as you saw from the repository. There are many other algorithms, but some of them are not based on Q learning. They're based on some other ideas. And so it's if you want to try out different techniques, and that's a good repository to start with. And there are many, many other resources. I think I've shared a wiki page earlier in one of the earlier sessions. You can start from there and get a feel for different algorithms. So we are here. So today's lecture is here. And so as you can see, there are two more, I guess, milestones to reach. The first one is the project report and related artifacts. They're due next Tuesday, April 27th, and presentations are going to happen during the lecture hours. And as I mentioned last time, for presentation at least, you want to focus on some of the interesting aspects for you of the problem that you picked. For example, like why use, how does it suit deep learning, for example, or your unique take on it, basically, for example. And it's not so important that you report performance numbers, but it's important to discuss, or at least convey useful information for the audience, right? They can always go back and look at a report. They can always ask you for the report. So focus on that in your presentation. Um, so what we're going to do today, and so that's pretty much my announcement. So what we're going to do today is, if you look at the short list here, so we're going to look at, actually, I'm going to pick uh, one topic from NLP. We actually did not, we looked at transformers, both the encoder side and the decoder side earlier. What I'm going to do today is just quickly go over a small example of how to use how to do transfer learning with NLP. So we have spent some time on doing transfer learning with in computer vision, right? So we know how to use ResNet, 18 or whatever it is, to and many other models from Torch Vision or elsewhere to jumpstart our training if we have a separate, we have an applied problem which is with data which is similar to ImageNet, for example, right? So similarly, attention-based architectures. One of them is called BERT or BERT. Was there a question? Okay, so there's one architecture called BERT. We're gonna not look at the architecture in detail, actually, since I want to cover a couple of more things. We'll just look at how to use BERT from a repository, sorry, from a package called transformers, and and that's what we'll do. Start with today, and then we'll actually spend time on unsupervised deep learning. Okay, so we haven't really looked at unsupervised learning at all in this course, except for one where we did latent digital allocation, but that's not a deep learning technique. So, and that was also for natural language processing. Here, we're going to look at working with images. And so we'll just look at two techniques. One is called variational autoencoders. It'll give you a sense of what's going on. So it's a little bit different from, you can think of it as yet another class of neural network architectures to be aware of in case it's useful, especially and we'll see some of the applications when we get there. And the second idea or concept is generative adversarial network. So both are useful for unsupervised deep learning. By the way, language modeling is also unsupervised. So word to vec or training transformers or training doing language modeling, for example, is actually unsupervised because you're not explicitly providing labels from some external source. You actually have labels which are the next word or things like that. So you don't really explicitly need, I guess, labeled examples. Okay. So that's the agenda. So we'll start with BERT, and then we'll get into unsupervised deep learning, basically variational autoencoders and GANs. Okay. Yeah, and let me also, since I'm here, let me also mention what the objectives are. So um, we'll probably not recall the key characteristics of BERT, but we'll at least learn how to use something like BERT as a pre-trained model for doing transfer learning in a specific NLP application. And we'll actually keep it simple. We'll only look at sentiment analysis, or basically a binary classification task. But the task is not so important. The important thing is how do we use a pre-trained model. And with unsupervised deep learning, or with variational autoencoders, we'll revisit what is meant by generative modeling. I think many of you have done know some distinction between generative modeling and discriminative modeling. We'll revisit what does it mean to do generative modeling and some applications of them, and then we'll look at what is the key idea behind variational autoencoders, and where can they be used. We'll also look at GANs, so intuition behind generative adversarial networks, the architecture itself, and of course, these types of problems you want to know what is the loss function you're optimizing for, how are you optimizing it, and what's the neural network architecture. Right? So we'll do that, and I'll talk about where they're used. Right, even for GANs, I will talk about where they're used when we get there. And finally, we'll end with if as time permits, we'll end with like differences between GAN and VAEs, because they tend to they can do the same type of thing. Okay. So yeah, and before I switch over to discussing a specific example, let me actually maybe I'll show these motivating or some related links later. So let me jump into the slide deck. Any questions about the plan for today? If any questions, to type it on the chat or ask me. So let me switch to a different screen share. Okay. So which slide deck is this? Is actually I think this is from. Oops, sorry. Good. 1 second. Okay. I think. Let me just set the settings. Bluetooth. Okay. So this is slide number 6, or module number 6. Okay. So yeah, for those who are searching for the slide deck, it's number 6. We are back to transformers, the deck which was talking about transformers. So in fact, I'm on slide 61. So we covered last time up to this point when we talked about transformers encoder side, the decoder side, and what goes inside, right? Self-attention and all that stuff. So we'll now talk about we'll now talk about transfer learning. Okay, so this is just a good point to do this, because I know some of you are working on NLP related projects. So if you want to use BERT, it's quite easy to try it out if that's something that you want to try as a variation. Okay? If you want to use a pre-trained model. So let's start with transfer learning. So, and in particular, we're going to look at a specific variant, a variant of a pre-trained model. It's called BERT, which has a full form. Okay? It's bidirectional encoder representations from transformers. Okay, so in short, it's BERT. So the idea is similar to how we can use pre-trained models in vision. So, and similarly, we have used pre-trained models in for language as well. In particular, word2vec and GLOW were essentially some sort of a pre-trained models, because for every word we were getting a vector representation. It was trained on some large corpus beforehand, right? But recently, you can actually use slightly different type of pre-trained models where the embeddings for the words, or in general your sentence, these vector representations uh, can be generated using transformer-based architectures, transformer-based models. And they have a few differences from the word-to-vec style generation of vector representations of words. Okay. And in particular, here I'm going to talk about a particular variant within this type called BERT. In particular, it's called distill BERT. It's just an extra, it's a variant where the number of parameters has been shrunk down to a manageable level, so you can import it in Colab or elsewhere. Okay. Generally, these pre-trained models in NLP are pretty large. Okay, and I think I mentioned GPT-3. It had 175, I guess, billion number of parameters, which is too many. Okay, so you can't even load that model on a off-the-shelf GPU. So what is the difference? I think I might come back to this later, but if not, the difference is this class of transformer-based pre-trained models, they give you contextual embeddings. Okay, so that's a keyword, contextual embeddings, rather than contextless embeddings. Okay, so word2vec and Glow, if you want to get a vector representation for a word like university, okay, so the representation for the word university is fixed, right? You learned on a large corpus, there's a vector, 300-dimensional vector. And it's the same thing, whether the word university appears in sentence 1 or sentence 2, it doesn't matter. The vector representation for university is the same. Okay. Unlike that, using transformer-based pre-trained models, you can actually get a contextual representation. So the representation for the word university will change depending on where did it appear in the sentence. So actually, you're generating these representations one sentence at a time in your usage. Okay, so you're not pre-generating the vector representation for all the words in your vocabulary in your particular problem, and you're done with it. It's not like that. Okay? You're gonna keep using this pre-trained model every time, for example, in your training loop, where you'll pass a sentence and you'll get a contextual representation for each word. Okay, that's what happens. So let's look at how to use such a model. In particular, we'll use distill BERT here. And before we actually see this example of using distill BERT, BERT itself, as I said, it was published in 2018, and it has been used in several products already. In particular, the Behemoth Google search. So and basically we'll look at a variation of it, and not just for Google search. It has been used for many different Google products, and not just for Google as a company, but many other companies have been trying to use such representations. Okay, you start with a very bad representation, one hot encoding representations or bag of earth, and then you go to some more I guess richer representations like word2vec and so on. Then you go to the latest class of representations like based on BERT and various other pre-trained models. Okay, so in particular, what we'll do in the next few slides is look at just a simple NLP task, which is a movie review classification task. It's equivalent to sentiment analysis, and many other such classification tasks that you have in NLP. So let's look at movie review classification. So what's the problem? It's basically you have a sentence and you want to say the sentence is a positive feedback or a positive review or a negative review. Okay, it's just a binary classification task. And your train data, let's say you've already created it and it has something like this, right? You have a sentence, a bunch of words, let's assume English for now, and and you've already worked with other languages and the difficulties with other languages before. So let's fix English, and you have these labels. Okay, so this is your train data, and the overall picture of how to use this pre-trained model is very similar to how you would use word2vec as well. Is as follows. If you want to do a forward pass, you basically have the sentence. You'll use this pre-trained model. It's like a function call, basically. This will BERT. That block is going to produce some intermediate representation. In fact, it's going to create a very simple fixed dimensional representation of the sentence. Okay, so some arbitrary length vector for a sentence, whether the sentence has 20 words, 2 words, or 200 words, whatever it is. This BERT is going to produce a fixed dimensional vector. In particular, we'll look at the numbers later, what dimension it is, and so on. fixed dimensional vector. And then once you have a fixed dimensional vector, you have a very straightforward classification task, right? So you have a feature vector of always, same length, and then you have a label, and then you can always apply, for example, logic regression or any of these gradient boosted decision trees or random forests, whatever you want. So that's the process. So actually, in that sense, this is pre-trained. So we're actually using this as in the feature extractor mode, okay, in the sense that we're not touching the parameters of this pre-trained model, okay. And in particular, the size in between here is going to be 768 dimensions. Okay, so that's the choice that was made for this particular pre-trained model. You can always, once you get this vector, you can always do hexadimensional reduction if you want, but but this is the vector size you would get if you use this particular pre-trained model. Okay. So let's look at some of the parts in this example will be very familiar to us. So we'll skip over some of these parts, but we'll focus on how to use this. Okay. So it's a little bit more implementation focused than idea focused right now. Okay. So the way, what does this first block do? So the block is basically trying to go from, let's say we have 2000 examples in our data set, okay, 2000 examples. Then this block is trying to just go from a sentence, each of these 2000 sentences to a fixed length representation, sorry. And as I said, the length is going to be 768 dimensions. Okay. And the contextual nature is basically that when, for example, you see the word funny here, the representation for the word funny, okay, and therefore the whole sentence, I would say, because we're only getting one vector for the whole sentence, whether the sentence is 2, then 2 or 20 or whatever. The intermediate, for example, the intermediate representation for funny when being constructed using this pre-trained model will be typically different from the same word in some other, in some other sentence. Maybe the funny represents to the movie. Funny is a word that's associated with the movie in the first review, whereas funny could be associated with the actor in another review. So in that sense, funny, the word itself, may have different embedding, may need different embedding depending on who it's related to and so on. So that's all captured here, okay, unlike word to word, unlike these other word embedding techniques. So I'm going to discuss this, the sentences at the top in a second. So let's not worry about it. So this is what we're doing. We're just going from a sentence to a fixed length vector. Okay. So and we'll do that for all the 200,000. Sorry, all the 2,000 examples in this illustration. Okay. And as I said, we're not going to fine tune this part, but you can always do fine tune. So I'm just repeating myself. We're going to be in the feature extraction type of transfer learning. Okay. So,
Professor.
Yeah.
Professor, you have a question. Yeah. So can you repeat again what the difference between BERT and other methods that you just said? The difference between
yeah. So I was just trying to say what's the difference between distilled BERT. Distilled BERT is, the adjective just means it's a reduced model in this class of BERT class of models. Okay. In general, BERT and the other ones, like GPT 1, 2, and 3, whatever, and there's others in the slide deck. You can look at that versus something like word to vec. The difference is that these are contextual. Okay, these are, I guess, fixed or non-contextual embeddings. Okay, so for fixed just means that, for example, for the word university, you'll have a vector, right? Let's say 300-dimensional vector. Okay. Some numbers, 1 minus 0.1, 5.3, and so on. Some bunch of numbers, right? So this vector is always the same for university. I mean, it's straight. University is a word in your vocabulary, and for that word you have a vector, and it never changes. Okay. Contextual embeddings mean that you're actually not storing a vector for each word and you're done with it. You're actually remembering this model. Okay, so this model, I call it just model. Okay. It takes the sentence, okay, the whole sentence every time, during your training or as well as test time, you actually use this model. This model will have parameters. You take the whole sentence, okay? You're not whole sentence. Of course, sentence will have let's say the word university in there. And the model actually produces a vector for each word, okay? Right? Each word in your sentence, okay? So let's say this is the vector for a university. So this vector, the entries of this vector can change depending on what else is there in the sentence. Okay? So it's contextual in a sense. If the word university was used in some other sentence, then the vector representation for university may be different. Okay. Is that clear? So we're not, so what we're remembering, what is fixed in word2vec is just a word2vec matrix, right? So for every word is a vector, that's fixed, and that's the pre-trained model. In BERT style thing, what is fixed is the model, okay? It's not the vector representation for each word that is stored here in this pre-trained model. It's the model, a model parameters, and then every time you pass a sentence, you actually get a vector for university, for something else, and every word in your vocabulary, for example. But what you pass is generally the sentence, and therefore other words in the sentence can influence the current word's representation. Okay. So for example, if I pass a different sentence and I look at the representation by university, it will be typically different. Okay. It's going to be a slightly different vector. Yeah.
Thank you. So it's not gonna consider all the sentences, right? It's gonna put one sentence in at the time and then provide a.
Yeah. Yeah. Contextual just means you're just trying to get a vector representation depending on what words, where it was used, where the word was used. Okay. And yeah, you get a vector representation for each word in a sentence. Here in this example, actually, what we're doing is a little bit different. For the whole sentence, we're getting a single 768 dimensional vector. Okay, and we'll talk about some details here why we're getting that. But in general, these pre-trained models, you'll get a vector representation for each word. It's just that the vector representation can change based on where the word appeared in the current sentence. Okay? Because what we're remembering from the previous corpus is just this model. As in word2vec, you will be remembering the word embeddings for each word in your vocabulary. Okay. Yeah, so we'll be passing a single sentence here, just to repeat what we said. So, yeah. So here, I mean, we're just saying, okay, we can split it into test and train set, and you do the usual ML. So here, I'm not really showing anything from here to here. It's just a train test split. Let's come back to, yeah, and here also I'm saying that if you have a training set, then you can just use some model, let's say from scikit-learn and elsewhere, to just train this model. Okay, so here just doing something like logistic regression. Okay, once you have these embeddings. Now, let's come back to how do we get these embeddings, and we're just thinking in terms of operational understanding here, not really digging deep into how distilled BERT model is trained from corpus, as well as what its architecture looks like. At the end of the day, its architecture is going to be very similar to what we saw before in terms of the description for the transformer architecture, okay, with some changes, of course. But we'll not look into the details of the model. We'll look into how to use the model in this example task, okay? And the use will be similar in other tasks. So let's come back to how do we get these embeddings, okay? This sentence embedding. Okay? We can have word embeddings, and once we have word embeddings, we can also convert it into sentence embedding, right? But we'll get a sentence embedding directly here, and the way we do it is as following. If you have a sentence, this is a pre-trained model, so we're not really thinking of training now. This pre-trained distilled BERT model. So given this sentence, what we're going to do is first tokenize. This is the usual operation that you do, and many of you've done this before. We're just splitting it into basically words or pseudo words, whatever you want to call it. Okay, we tokenize, and then we add some special tokens. Okay, these are the CLS and SAP separator tokens. These are just tokens that you add, and this is a convention. These are tokens that the model understands what these tokens mean, and it is just special tokens outside the vocabulary, basically. Okay, you add these tokens. So basically, what you're doing is you had a sentence from which you tokenized. You got a bunch of tokens, right? Yeah, a bunch of tokens, and then you add a couple of more tokens. Okay, so which is the CLS and separator CP tokens. Okay, once you have this, you just pass it through the transformer. Okay, so sorry. Once you have these symbols or these elongated tokens, you convert them into indices, right? You get the token index or basically the numbers corresponding to each of these words, basically. Okay, so you get these token indices. Okay, and once you have these, then you pass it through the BERT model. Okay. You pass it through BERT model, and in fact, the model is actually taking these tokens, so these numbers as input. Okay. And very similar to the transformers encoder architecture, or the encoder model, if you remember, encoder was taking all the words at the same time and producing some vector representations for all the words at the end of the day. Okay, even whether it was a single encoder unit or the whole encoder architecture, at the end of the day, you pass all the words together and you get some vector for each word uh, as an output, right? So that's exactly what's happening here. So we have these uh, tokens, we pass their indices basically. And then what we get is a vector for each word, right? So one vector for each word. Okay. And each vector is actually 768 dimensions. Each vector has those many dimensions. That's predetermined because of this model, but if you had a different model, it would be some slightly different number. Okay. So what we do is once we get these vector representations, remember, so this is like the transformer encoder block. So every, so let's say there were 6 encoders for simplicity. Then each encoder unit here, sorry, not this, on the other side here. So inside that, maybe encoder number 1, encoder number 2, encoder number last one. And within that, if you recall, from several weeks ago, we talked about self-attention and then a feed-forward layer. So within each encoder unit, right? So all the words were inputted at the same time. Each there will be one vector corresponding to each word that will pass to the next encoder unit, and similarly that will have its own self-attention and fully connected feed-forward layer, and so on. Okay. Very similar idea follows here. Okay. Of course, the architecture for the BERT encoder is slightly different from the transformer architecture that we saw, but the same idea applies of self-attention and so on. So that's what's happening here. So each representation here of the word or the token is dependent on everything else. Somehow it depends on everything else. Okay, all these previous words. Okay, so every representation is like that. Okay, what we'll do is pick up the representation only for the CLS token. Okay, that's the way this pre-trained model works. Okay, and that token somehow represents the whole sentence. Not somehow, we know that that token is determined by all these guys. Okay, why does that token represent the whole, some information, some, I guess, the right information in the sentence? Is just because of the way the DistilBERT was pre-trained, and we have not talked about it, how these pre-trained models are actually trained from corpus. In the word to vex case, we did talk about in detail how word to vec itself is trained, but for DistilBERT we have not talked about how it's trained. Okay, there are a couple of tasks that is trained on, because of which it turns out that this token, when added at the front, does capture information about the whole sentence. Okay, but let's not worry about that. And this is the key step. So basically, you pass tokens, you get representations for each of the token. You only care about the representation for the top, first token. Okay? And that's going to be 768 dimensions. This guy. Okay? It's going to be 768 dimensions for this particular model. And that's it. And once you have the 768 dimensional vector for each sentence, then you just proceed forward with that vector, okay, in whatever downstream task you're doing. For example, this classification task here. So yeah, I mean, what I just mentioned, what I just said is captured here. So we have this input, and here we're just calling it as model 1 and model 2. Model 1 is this pre-trained DistilBERT model. Model 2 is the logic regression model, for example. So model 1 produces a lot of outputs, but we don't care about all these other outputs. Okay. If you wanted word representations, for example, these outputs would matter. Okay. If you wanted, this is where I guess the contextual embeddings is what I mentioned. So if you want a representation for the word stunning, the representation for stunning depends on all these other words that appeared in this sentence. And if stunning was used in a different sentence, its representation would be slightly different. Right? But what's fixed is this guy's parameters. That parameters is fixed. You can also change it if you do a fine-tuning style of use of pre-trained models, right? But we are not talking about that here, but you can certainly do that as well. Very similar to what you did in assignment 2. So model 1's output is this vector, 768 dimensions, and then you just pass it on to the next model. And this is the model that you train. Okay, this is basically you just train it in a separate stage because you can always create these vectors for all the sentences together. And then once you get these vectors, you have a simple training data of features, comma, labels. You can always do this logic regression model or equivalent in a separate step. Okay. Now,
Professor, can you go back? So can I take another, for example, another vector to put in the second or just the first one?
A different vector? Yeah, I mean, so it just happens that this is the vector that captures sentence information. I mean, as I said, remember all these other outputs are supposed to capture contextual embeddings of these words. Okay, so whereas this is actually not a word in the sentence. Okay, there's a special token that was used while training, such that this token has information about the sentence. Okay, so I guess you can use this separator token or SCP token, but it just turns out that this is the right token to use. Okay, and for why is that the case, we'll have to look at the details of the model, and we are skipping that. Right, but just imagine that these other tokens, most of them would be representations of the word itself.
Okay, got it. Thank you.
Okay, so let's move forward. So let's look at, so since I just explained how that's done, so how is it done in code, right? So the code is quite straightforward, especially the most important, I mean, the parts that are relevant to us is that's import. Okay, import transformers. Transformers is this nice, easy to use library that has these pre-trained models. Okay, so we are importing it as an object here, and then we're just calling the model. I mean, we're calling two classes. We're defining two classes, right? Distill BERT model and distill BERT tokenizer. Those are two things that we are getting. And we're also getting at, we're just creating a string here. So these three things are being defined as model class, tokenizer class, and pre-trained weights. Okay, pre-trained weights, just think of it as a string. Okay, so it's just a multi-assignment equal to a multi-assignment. So it's just model class is equal to the first thing, tokenizer class is equal to second, ppb.distill BERT tokenizer, and pre-trained weights is a variable that holds a string distill hyphen base hyphen uncased. Okay, so it's just three assignments happening in parallel in one sentence. And if you want a slightly different instead of distill BERT, if you wanted the BERT model itself, then you just call the other classes, okay, the related classes, BERT model, BERT tokenizer, and the appropriate variation for the string. What does the string do? It just picks the right parameters. It lets you pick the right parameters when you define the model. Okay, so what we've done in this sentence is just get the classes. Okay, the model class and the tokenizer class. Now we want to create an object from the model class and the tokenizer class, and that's done here. Okay, so tokenizer is just tokenizer class, and define it using the appropriate pre-trained model string. Okay, so this is the distill BERT based uncased type. So for that, we need to create a tokenizer. We create the tokenizer object. Similarly, for the model class from pre-trained, and the string is distill BERT hyphen base hyphen uncased. You just create a model. So this is very similar to ResNet 18 or ResNet that you created while working with vision. Okay. So once you have the tokenizer in the model, then let's say you have a pandas data frame for your movie review data set. So basically, these are the indices, and there are three columns here. Sorry, two columns here. Column 0 is the strings. Okay, is basically a string with these words, and column 1 is this numerical data type, 1 or zeros, right? So what you do is so you have this data frame, right? So data frame bracket 0 would give you the first column, okay? Or if you had a column name like review, and df bracket review or df.review would give you the that pandas series, right? So you know how to do indexing with pandas. If not, don't worry about it. It's just we are just picking these guys, okay? This column. We're picking that here, okay? df series. And then dot apply is a function that's available with a pandas data frame. What you can do is apply a function element wise, or apply a function for every row in that data frame. So what we do is and there's also this notion of a lambda function. We haven't seen lambda functions explicitly in the sessions, but lambda functions is just unnamed functions. So it's a instead of lambda function, you could use some other function here, okay? Some other defined function here, like def, the function name. What it does is take every row element, okay, every row element, take x, and apply the tokenizing step. Okay, so tokenizer.encode on this x, which is the input string, right? So every row is a string of is a review, which is a string of words. And then you also say add special tokens. Add special tokens adds the CLS token at the front and the separate token at the end. That you can see here. So what you get is, after the step, you get a tokenized data frame. Basically, yeah, you get basically a list of tokens. Okay, and what you do is, okay, so next, let me just briefly mention that you also, the maximum sentence length, this is a pre-trained model. So, if you remember encoder of a transformer architecture, the number of words, you need to pre-decide how many number of words you parallelly, should be there in any input sentence that you're going to work with. Okay, so for example, in the running example that we were looking at when we were talking about transformer, it was 20 words. Here, this BERT, it can work up to 66 words. Okay, that's fixed. So the way you're gonna, so the way when you create these tokens, so you'll have to pad, right? So not all sentences will be of length 66 words, and many of them will be shorter than that. So the remaining word locations you have to give like a default token, like 3. Yeah. So basically, you want a padded version of this list of tokens for every sentence. Once you have padded it, you can always convert it into a array. So I was talking about list of lists. Instead of list of lists, you can you basically get a matrix. Okay, so the matrix, the number of columns should be 66. Number of rows should be the number of examples that you have. For example, 2000 in this illustration in this slide deck. Okay. So you have this NumPy array. You convert it into a torch tensor. Okay. And that's going to give you this tensor. And then you just forward pass in this pre-trained model through this pre-trained model, this is BERT model. Okay. And if you do a forward pass, you'll get a bunch of representations. I think we just discussed this, a bunch of representations. We just need to, if you remember, we just need to pick the first token representation for each of our 2000 examples. Okay, that's what we're going to talk about next. Okay. So it turns out that this last hidden state, so the output from this model's output, the 0th element in this list of outputs is the block. Okay, the 0th element is not super critical. It's just a you can look at the output and figure out that what is the tensor to work with. It's just the 0th element. 0th element turns out it has 2000 rows. Okay, and 66. I guess the second dimension 66 because there are 66 words, and for each word there's 768 dimensional vector. Okay, so those are the 3 dimensions in this output tensor. If you recall, what we want is just instead of, so if there are 66 tokens, so 66 words, we just want the 768 dimensional vector for the first word. Similarly, the second 768 vector for the second word, second sentence, and so on. Okay, so we just want the one slice of this tensor. Okay, and that slice is basically for each sentence a vector representation of that sentence. How do we get that? I mean, I'm just showing it here in this example. So let's say we had this vector of tokens or a row in this NumPy array, added NumPy array. Then what we get for the first example is this slice, right? This slice. What we want is just the first one vector of this slice. Okay, just this vector is what we want. And that's it. And similarly for the second slice, we want the same, the same left side vector and so on. Okay, so How do you index that? It's very easy. I mean, you have this output model output, just index it by, since it's a tensor, you can just index it like this, and you'll get back this relevant part. Okay, this relevant part here. And that's going to be your sentence representation for each sentence, and there are 2000 of them, 2000 rows, and so and beyond that you can just use them, and this is your the flattened view, and this is what you can use for your training. Okay, so yeah, I mean that's going to be, once you slice it, it's still going to be a tensor object. You just convert it in NumPy, and if you want to use it in a scikit-learn style workflow. So any questions here? I mean, I'm not going to talk about training. I mean, once you have this embeddings, it's very straightforward way of training the model. So I will not talk about training a model. For example, you can use logic regression, you can use random forest classifier, any of that sort. So we're not going to talk about them here. Right? Yeah, it's just x comma y pairs, and so you can always do a lot of things from this point onwards. Okay, so that's how you use it. So as you saw, it was pretty much 5 lines, importing transformers library and defining the model in the tokenizer, and just, if in the feature extraction style of doing transfer learning, you just have to get a embedding for each sentence. Okay? And from there onwards, it's pretty much conventional machine learning. Okay, so if there are no questions, then we're gonna skip. We're gonna switch topics to unsupervised deep learning. So if there are questions, you can ask now. I'm going to switch slides in the meantime. Okay, so let's actually then switch topics. So the outline for the rest of the session is as follows. We're going to briefly motivate ourselves or recall what some unsupervised learning is about. Mostly, I mean, of course, we're going to spend a little bit more time on deep learning perspective, and then we'll talk about 2 specific architectures or 2 specific model classes. One is called Variational Autoencoder, and it's closely related model called Autoencoder, and that's different model family called generative adversarial network. So, and these are acronyms, and I probably use acronyms quite a bit. So these are the names we'll use. Okay. So we all know what's the difference between supervised learning and unsupervised learning. Basically, unsupervised learning, we basically have just feature vectors. We don't have labels, annotated outcomes to use. And examples include images or even just plain text that you scrape from let's say Wikipedia or something like that. This is all unlabeled, right? At least in the raw form. And the goal is to learn some patterns of the data for some downstream use. And when you learn these patterns, there's actually no objective measure of success. Okay, you will have to define, like in supervised learning, there is this out of sample error that you use to figure out whether you actually built a good predictive model or not. Here, there is no such objective measure. There are, of course, many. You can always create some measure yourself and call that as a way to see whether you succeeded in learning some patterns or appropriate thing to use for your downstream task. Okay. So let's actually look at some of these tasks, and they all have different subjective measures of success. Some of the things that you might have already seen in your previous other courses are clustering, association rules, using PCA for dimensionality reduction, and density estimation. Okay, learning the mean and variance of a one-dimensional Gaussian using, for example, maximum likelihood estimation. Right. So you might have looked at it. If not, it's not a critical thing that we need to know this, but there are these methods. Okay, what we'll see today are going to be, we're going to spend most of the time on sampling, but embedding is also a embedding as in representing your input x using another variable, something like z, is useful. Okay, so embedding is just going from some input to some output, right? So we saw word to vector, we are embedding words. So for example, embedding is as simple as going from images to vector representation of images, but we can do that without knowing the labels of images. Okay, so whereas you would have gotten these embeddings from, let's say, ImageNet, let's say AlexNet, or one of these BGG16, but those were trained with labels. Okay, so we don't want to use labels here. Here's an example clustering. For clustering, one of the popular algorithms is called k-means, and here's a very simple two-dimensional clustering example illustration. Similarly, association rules, is related to something called market-based analysis. It's basically trying to find most frequent subsets of events or items, or coordinates, or particular feature values in a data set. Okay, so that's association rules. And dimensional reduction, it's about going from higher dimensions to lower dimensions, and we'll see actually autoencoders are also about dimensional reduction. Okay, dimensionality reduction. So we'll look at dimensional reduction in a second when we look at autoencoders. But it's all about just going from a higher dimension to a lower dimension while retaining maximal information in your data set. Okay. Dimensional reduction. Density estimation is about estimating the parameters of the. So you got some data from a probability density from some unknown object, from the environment taking measurements. You don't know what that original source of data was, but you can always fit a probability density function, right, or a probability mass function, whatever it is appropriate. You can fit such a density function to say, hey, this is the distribution from which these samples or these examples might have come, right? So that's density estimation. So it's typically, for example, the most, I guess, familiar one to you is going to be doing maximum likelihood estimation. So for example, you have a bunch of observations and you want to say, hey, I want to fit the mean and the, so you can always compute the mean and the standard deviation, right? Once you can compute the mean and standard deviation, you can say, hey, this, I can approximate the original data with a normal distribution with this mean and with this standard deviation, for example. You can do that. Okay. So that's density estimation. We look at embedding. Okay, so this is where I said we don't have to have labels. Let's say we're working with images. Okay, we don't have labels, but we can still get lower dimensional vectors for these images. Okay, or some vector representation of these images. And how do you do that? You can. We're going to talk about one example. This is just a very small slide or quick illustration. I'm going to talk about a little bit more about this in a second. It's called autoencoders. Okay. What's happening is you have your original data, it's somehow getting transformed to another data, another variable called z. So x is getting transformed to another variable called z, and z is like an embedding. Okay, z is like your low dimensional vector or some sort of vector representation of your input. Okay? If your input is an image, you can get a vector for this image. We don't need labels. Okay. Certainly, these embeddings are going to be different from the embeddings that you would get from, let's say, from something like ResNet 18, but at the same time, these are useful in their own right. And finally, sampling. Sampling is, and we're going to really talk about some challenging data sets here, right? So we're going to look at these unstructured data sets that we talked about, images, let's say, or text. The sampling is about generating new images. Okay, new images are not just like existing training data or existing images and add some noise onto them to get new images. It's not like that. So you somehow create, you have a training data of images, convert them into an object. From that object, you want to, if you call dot sample or or something like that, you should get a new image, which is not just a noisy version of one of your training data examples. Okay, you want something which is hopefully new. Here is a quick illustration of, these are not really good images. These are actually from data from Pokemon Go. That was the original data from which an object was constructed, from which you are sampling images. It just turns out those images retain some characteristics of input data, but they, of course, they don't give you no new characters, for example. So, but we'll focus on these two. In fact, predominantly on the last part, which is about sampling today. Any questions at this point? I mean, about all these techniques?
Professor, I have a question. It's not regarding this. I just
Mhm.
wanted to know if we can still access all these videos. Will you be uploading it to YouTube? Because I've seen
Yeah,
that you have uploaded the previous. Okay.
yeah, you'll have, of course, you'll have. Yeah,
Okay.
Zoom has an expiry, right? It has 180-day expiry or something, half a year expiry. So yeah, you'll have access to it. Yeah,
Okay.
we can
Thank you.
discuss offline if you want the offline way of getting these videos.
Okay.
So
Awesome.
let's continue with the sampling part. So what we want here is basically, let's say there's some data, and we typically want large data for this, especially with images. So given some data drawn from some potentially unknown distribution, PD, P subscript D represents data. Okay, we want to estimate some model, okay, PM, okay, some model, and here we're calling PM as a model instead of so far in our in our vocabulary, model always means, hey, given input X, predict something Y, right? So here I'm just saying, I'm even calling PM as a model. It's just a distribution. It's some sort of an object from which I can get new samples. Okay, PM, M represents model, so it's modeled. It could be parametric, for example, like a Gaussian distribution, it's a mean and variance parameters. Okay, such that we want the samples from the model to be almost, similar or in some sort similar in flavor to the samples that were observed. Okay, so if the original samples were images, I want new samples which are new images, but they have to be images. Okay, they have to be as if they are of some real object, for example. That's a very hard thing to do. And people are still trying to solve the problem. Try to build good and good, better and better models to achieve that. Um, so two approaches to get to PM. So we have PD. We don't actually have direct access to PD. We have data from PD. This distribution governance data, our data generating source. And given the data, we want to construct this object from which we can get new samples. Okay. Um, there are two approaches, an explicit approach. Explicit just means there's an explicit way to have a PM object. Like, for example, the normal distribution with some mean and variance. This is an explicit object. Okay. There's also another approach called implicit approach, where we are not where we're actually creating an object which is not exactly PM, but it's still gonna generate samples for us. Okay, it's still gonna generate samples for us. It's not going to be PM though. Okay, it's not going to be this approximation of the original data generating distribution. Okay? And for us, we are not really concerned about this distinction between implicit and explicit type of approaches to generating samples. But here's a I guess tree of different techniques that was shown in this tutorial by this researcher. And what we're going to look at is GANs, okay, which are one approach, and we'll also look at variational autoencoders, which is the third approach. But at the end of the day, we want some object from which we can sample new images. Okay, so that's the goal that we're trying to work towards. Uh, yeah, let's not worry about the difference between explicit and implicit images, explicit and implicit approaches. Um, we just want, I mean, so in this slide, I don't want to talk so much about explicit and implicit approaches. I'm talking about more about what are the uses. Okay, so for example, one use of such as any such object is going to be to generate these samples, which can be used for example, planning. Okay, so you can generate, for example, think of an object or some sort of a function from which you can generate trajectories of how future price movements will be for a particular stock. Okay, so if you can get those trajectories samples, then you can plan your, for example, asset allocation strategy. Okay, so something like that. And you can also, if you get samples of images, you can also use that for some, let's say, downstream creative process or some, maybe downstream process that you want to work with, okay, where you need fresh or new images. So for example, here, these are actually images that were generated. These are not in the training data. And these are not just slight perturbations, adding noise to some previous existing training image. Okay, these are supposed to be freshly generated. And so, in fact, these images may not even look correct, okay, in the sense that they may have some obvious issues in the image, but they look natural. Okay. there are other uses of there are other uses of learning such objects, these sampling objects. Okay, one example is if you can create this sampling object from a large corpus of images, then given an original, there are some extra steps involved, but given an original, I guess, a lower resolution image, because you learned this object which was on potentially on high resolution images, you can actually improve the resolution. Okay, that's one example. Of course, there's some extra steps needed here. Let's not worry about this. Uh, Extra steps needed, but in that sense, that such a sampling object is useful. So um, here there's some names here, but let's not worry about it. But I'm just saying that here, this is called image super resolution. It's going from a low resolution image to a high resolution image. And how can you go from a lower resolution to a high resolution image? You can do that with an intermediate object, which has seen many such high resolution images. Okay, something like that. So that's one application. Generally, there are many applications. For example, going from a satellite imagery to a illustrative imagery, or doing from going from a labeled scene to a real scene, or going from a text, a sketch to a real object. You can do all these, and these are not something fictitious. These are people, researchers have tried to various degrees of success to achieve such input-output, such transformations. Okay, where it's not like you're learning you're learning these representations using supervised learning. Predominantly, it's using techniques that we'll see today. For example, GANs. And maybe during the break, I'll show you some videos of these applications. But let's come back. Although there's this explicit notion of, hey, there's an explicit approach to creating the sampler, this object from which I can sample new images. There's an implicit notion. But the important thing is we're going to look at VAEs first and then GANs first, GANs next. And both will use neural networks as a centerpiece in their implementation. And of course, we're going to work with image data mostly for the rest of the session. And yeah, so those are the two things that we're going to do. Any questions here? Okay, let me tell you one more thing, which is, as I was saying earlier, we're not just creating, when we create samples of new images, these new images are not supposed to be just slightly noisy versions of the original images. Okay, we want to do more than memorizing your training data set of images. Okay? You're really creating truly a new image. Okay, so let's say you have 1,000 images of cats, and you create this object, this GAN model or a VAE model. If you sample from them, you should get a new cat, ideally. Okay, and that seems very implausible at the beginning, right? So, but they try to do that, and they have achieved partial various degrees of success doing that, and that's why we're studying it today. Both models work in a fashion which is going to be as follows. Okay, so the way, and since they have to be samplers, there has to be some sort of randomness, right? So if you draw a sample from a Gaussian distribution, sure, you can that's a sampler, right? But here we wanted to sample images, so you can't. So what does this object look like? So it needs to have some sort of randomness, some sorts of initial randomness. So that's achieved by starting with some sort of a Gaussian distribution. You get a Gaussian vector, okay, some vector, z vector, from which you pass through essentially a neural network. Here we're just calling it generative models, but it's basically a neural network. And we'll talk about these two, by the way, in a lot of detail. But at the end of the day, what I'm saying is both these approaches, VAE and GANs, will give us, for example, this yellow block, okay, just generative model or a neural network. And the way you generate these images, these new images, which were not there in the training, is you start with a random vector. Okay? You draw a random Gaussian vector. Okay? Similar to drawing a Gaussian scalar, you can always get a Gaussian vector. You get the vector, pass it through a neural network. And actually, at the end of the neural network, it's actually going to produce an image. Okay, it's actually going to produce an image. Okay, and the image, okay, this part is just showing that the image, you can draw many such images. If you draw many such Z's, you can draw many such images. If you actually illustratively think of what the distribution of the images is, maybe the image distributions is like this. Okay, it's very hard to imagine that because images, how do you even represent images? And let's say images were representable by vectors, then it's like a high dimensional distribution in some high dimensional space, right? It's a distribution in high dimensional space. So what these models do is somehow approximate this distribution, right? That's what this PM, right? Approximating the distribution, and you have actually the true data distribution from which you have images, right? So those are the ones we use to train this model. And those are, for example, shown by the stars. So this is PD. You don't know PD, you have these images, 1,000 images, 100,000 images, whatever it is. And from there, you've created this yellow block. And then how do you use this block? Start with a random source like Gaussian distribution and produce an image. Okay. And if you produce many such images, there'll be some approximating distribution that you are trying to you get. Okay. I mean, it's hard to actually the one inside this the block. We are actually not going to evaluate the goodness of our model by looking at this. It's very hard to do, but this is what we are doing. Okay, so we are starting from a random vector and creating an image. Okay, at the end of the day, what we'll spend most of the time today is not this forward pass, but actually the training part of both VAEs and GANs. But once they're trained, there's going to be something like a yellow object, which is essentially a neural network, which goes from a vector to an image. Okay. Any questions? If not, let's start with autoencoders and variational autoencoders. So autoencoders is just a warm-up for us. We are not so concerned about autoencoders. It's related to variational autoencoders. It's a motivating thing. It's useful to include it here, but we want to spend time on variational autoencoders first more. So for that, we'll take the following aspect as a fact. Okay, we'll not investigate too much. Which is as follows. Okay, a neural network is just a function, right? It's just a function going from a vector to maybe a bunch of scores, typically, right? Maps an input and output. You can actually go from a vector to an image. Okay, and that seems, hard to imagine on the first try, because if you remember CNNs, you're going from an image to a vector, which was a vector of scores, right? But what I'm trying to say is that there is a way to go from a vector to an image, okay? A vector to an image, okay? And that, although it seems surprising, it's not actually that surprising. You are basically saying I can go from a let's say 100-dimensional vector, right? 100-dimensional vector to a 64 cross 3 cross 64 cross 64 cross 3-dimensional tensor. Okay. So I'm going from a bunch of numbers to another bunch of numbers, and that should not be surprising. Okay. In fact, the particular representation here, it's called a deconvolutional network. Actually, the right terminology to be used is a transpose convolutional network. Okay. It's going from a vector. Okay, it's I guess one tensor, small tensor, to a degenerate tensor, to another tensor, another tensor, another tensor, another tensor, and eventually a tensor which has three depth. Therefore, it's an image. Okay, so that's something that will take us granted, because this is how. So if you recall the generative block or the generative model, it's going from a Gaussian random vector to an image, right? And this is how it will look like. Okay, so these intermediate transformations, these are, you can call it the decon layers or transpose convolution layers. Okay. We'll not spend too much time on it, but just to point out that how do we get from a smaller dimensional vector to a higher dimensional vector? It's not difficult, right? So you can actually, for example, here is a simple example. If you had a 4-dimensional vector and you want to go to a 16-dimensional vector, what do? You multiply it with a matrix, which has 16 rows and 4 columns. Right? There's nothing complicated going on here. And on the left side, you can see there is a 4 numbers or a 4, there's a 2x2 matrix. So if you expand it out, it's a 4. If you just vectorize it, it's a 4 length vector. At the bottom, you have a 4x4 matrix. Okay, you want to go from top to bottom, right? Top matrix to a bottom matrix. So in the bottom matrix, you have 16 numbers. In the top matrix, you have 4 numbers. How do you go from the top to bottom? You can actually just do a linear transformation. Okay, and this is what's going on pretty much when you think of going from a higher dimensional vector to a lower dimensional, sorry, from one tensor to another. Okay. Yeah, any questions here? We don't want to investigate too much about this, but all I'm trying to say is that going from a vector to one tensor to another tensor, even if the starting tensor is a smaller tensor to a bigger tensor, it's not, it's not rocket science. I mean, it's not something impossible. You can always do it. Of course, there's going to be redundancy. Okay, for example, this matrix is at most rank 4. Okay, so the rows in this matrix, they can only be 4 independent vectors. Okay, so but that's fine. But more than that, you can actually go from any vector space to another vector space. Let's actually now talk about autoencoders. So what I'll do is not use the next couple of slides, but actually directly get to this slide, okay, because the previous 2 slides were just motivating how to get to autoencoder, but I think this slide is a good starting point as well. So what do we want to do? So what is an autoencoder? Okay, so what an autoencoder, remember we are in unsupervised learning paradigm for the rest of the session or in the session. So an autoencoder is a way to get an embedding for your input data. Okay, so think of PCA. Okay, PCA is getting an embedding for your data. Okay, of course it's trying to reduce dimensions. So this embedding or this output vector that you get and after you do the PCA process, it's a lower dimensional representation of your higher dimensional data. Right? So if you're a feature vector which is 100 dimensions, after you do the PCA process, you get a feature vector which maybe is 5 dimensions. Okay. So similarly, in autoencoder, the objective is to capture information in this original data, okay, using a smaller dimensional vectors, okay, using smaller dimensional vectors. And so in particular, we're going to call them latent vectors or latent variables. Okay, so what we want to do is go from a high dimensional vector to a smaller dimensional vector. Okay, so in between, if you remember, you can always use PCA as a benchmark. If you remember, if you do PCA process, you can always get a lower dimensional vector to a higher dimensional vector. Okay, each of the high dimensional vector in your training data. Similarly, the same idea is what we want to do here. We want to get these lower dimensional vectors. Okay, and as I said, of course, we want to get lower dimensional vector. We keep the dimension of z smaller than x, okay, input x. Okay. And let's not worry about this point. This is not very critical. So, but you can see, but the way we're going to get these vectors, the way we're going to get these lower dimensional vectors is going to be different than what we saw with PCA. With PCA, we actually have to do that SVD operation or this eigen decomposition of what you want to do. And then you can get these principal component directions and principal component stem cells and so on. Okay? But here it's going to be different. In fact, we're going to use neural networks here. So how do we, and for that, and this type of picture you'll see for the next few minutes. So it's good to see that. So there's going to be an input layer, sorry, input data. Okay, that's going to get converted to a low dimensional vector. That's going to be up converted. Okay, that's going to be converted back to hopefully the original vector. Okay, and by trying to go from a high dimensional vector to a low dimensional vector and low dimensional vector back to high dimensional vector, and hoping that these two are similar, hoping that, as I said, try to change the parameters of neural networks involved to make these two reconstructed vector the same as the input, is how you do how you get these embeddings, how you get these leads. Okay. So let me explain that with a more enlarged figure. So what you do is go from x to a z. Okay, so there are many x's. Let's say you have a training data which has 1,000 samples, okay, 1,000 examples. Then you take the first one. There's going to be a parameter for the encoder, a parameter for the decoder. Let's call it theta1, theta2, simplicity. So there's going to be some encoder which is going to go from x to z. There's going to be some decoder which is going to go from z to x hat. And then you say, hey, this x hat I want to be close to x. So in particular, what I want to write is x minus the decoder with parameter theta2 of encoder with parameter theta1 of the original x, some 2 norm square. So this is just think of it as squared error, or least squares error, or something like that. So this is what you want to do. You want to minimize this over theta1 and theta2. Okay. So yeah, and you can sum over all input x's. Let's say this is xi, then I is equal to 1 to n. Okay, whatever number, 1,000 examples that you have. So this is exactly what we're trying to do. And now you have an objective function. You want to train, you want to learn the theta1, theta2 such that xi encoded and then decoded is almost the same, hopefully the same as x itself. Okay, that's essentially what an autoencoder is. And the autoencoder name is because you're encoding x, such that it produces x itself. Okay, so that's an autoencoder. That's how the name arises. Any questions here? Okay, if there are, certainly use the chat. So it turns out, so whereas the neural networks, right? So this decoder and the encoder are actually neural networks. So if you just used a single layer, no hidden layer neural network, no hidden layer neural network, then this is essentially equivalent to a PCA. It's not the same PCA, but it's equivalent to a PCA output. Okay. So what do I mean by that? So you have, let's say you do a linear transformation. Okay. Let me not use, you do a, actually, let me just use W. So you do a linear transformation. Okay. Then you do, this should be, let's say is equal to C. And then you do another linear transformation. Let's call it W prime of Z to get X prime. Okay. These are two linear transformations. Z is a lower dimensional number, lower dimension vector. X is a higher dimension vector. Then X prime is equal to W prime times W times X. Okay. And then we're just saying, hey, can you reduce the error between W prime or W matrix as well as W prime matrix? Can you do this? Okay. This actually, it turns out it's very similar to the PCA objective. Okay. The PCA objective has a slightly different, slightly extra constraint that the turns out these matrices here are like the eigenvectors of the data matrix, of the covariance matrix, or the left singular vectors of the data matrix. Okay. And so since they're singular vectors, they have this some sort of orthogonality constraint. Okay, so the vectors need to be orthogonal to each other. The vectors as in the columns in the W matrix, for example. But let me not go into that detail. All I'm saying is there's a relationship between autoencoder and PCA. If you have no hidden layer neural networks, for example, very simple thing like this, then it's almost equivalent to a PCA. Okay. So wherever you use PCA, you can also use autoencoder, but you can imagine, hey, why should I use a simple, why should I go from X to Z using one, matrix, right? I can do a matrix, a nonlinearity, another matrix, a nonlinearity, another matrix, and so on. So that's essentially a full-fledged, deep learning with autoencoder, right? So you have bunch of layers going in the encoder, bunch of layers in the decoder, then you have the full-fledged autoencoder, right? But this autoencoder is just for embedding though. So just like PCA, we are just getting a smaller dimensional vector representation. It's a nonlinear dimensionality reduction technique. So you get a smaller dimensional vector. Okay, so you're not generating samples, but this is a warm up for us. Well, we go into this variational autoencoder architecture. Okay. So let's talk about variational autoencoder. So the name variational. So the variational autoencoder, the whole point is, hey, the previous thing was embedding, going from X to Z, and then Z to X hat. So those are embeddings. At the end of the day, autoencoder is just going to give us embeddings. What we want is a generator. We want to give a random vector as input, and we want to get a potential image, X hat, or some new image, okay, which is not there in the training data, okay, as an output. So that's the objective. So for that, we necessarily need randomness, right? So the previous process was just a simple minimization problem. There was no random variables and stuff. But for variational autoencoder, we'll not start talking about random variables. Okay, so we're going to have a random variable Z, and we're also going to call a random variable X. Okay, there's going to be two random variables. So it's like, it's basically, this is, by the way, this is called a graphical model. And we have seen a graphical model. We've talked about LDA before. as well as when we talked about naive-Bayes classifier. But anyway, a graphical model is just a um, is just a distribution of random variables with a graph that can illustrate how the distribution looks like. So here, what I'm trying to say is that there's two random variables, z and x. So there'll be basically a distribution on z and x. So what is x here? Think of them as images. What is z here? Z is going to be some sort of a latent random variable. Okay, we haven't. It's not images. Okay, it's some latent random variable. It's associated with x. And why do we want this type of graphical model? Is because, hey, if I can make z, for example, a normal distribution, okay, then what I can do is, this p of z comma x is equal to p of x given z times p of z, right? If I can say, hey, z should be normal distribution. Let's say I want to externally impose a constraint. Z is anyway not there in the data. I am, arbitrarily, conceptually adding it. So if I can make z to be a normal distribution, for example, so I can then sample from z, and then given z, if given z, pass it through essentially some sort of a neural network, right? So if I give z as an input, I can produce an x as an output. Then I can generate x. Okay, so that's the reason why we are adding this extra latent random variable z. So yeah, so let's come back to variational autoencoder definition first. So as I said, there are going to be two sets of random variables, z and x. And the intuitive idea is to have this latent random variable. Latent in the sense it's not visible and it's not there in the data. Okay. From data, we want to get to this object, which is a sampler, from which we can sample new images, remember? Right? So to do that, what we want to learn is the parameters of this graphical model. So we want to learn the parameters of the graphical models, which means the parameters, there's some parameters here. We learn the parameters of the graphical model. We learn this, and of course, there's going to be thetas here. Then we can sample from z. Let's say we further restrict z to be Gaussian. That's something we can choose. Then we can, since we learned the parameters using data, okay, then we can generate x's. Okay, so once we know the parameters, we can generate x's. So there's going to be, so the way I'm going to describe it, first I'm going to describe, there's going to be two changes, and maybe we'll talk about the loss function first and then the architecture next. Okay, so there's going to be two changes from what we saw in the autoencoder. So that picture of going from x to z to x hat, that's just a warm up, and we'll see a similar picture here when we talk about the architecture. But before that, let's look at the loss. Okay, and the loss is basically similar to what we saw earlier. So earlier I said, hey, something, a loss function like this, is enough for us to learn these embeddings, nonlinear reduced dimension vectors. Right? So let's look at the loss first. It turns out that variational autoencoder is at the end of the day, there's some loss function you want to optimize, because at the end of the day, you want to learn the parameters of a neural network. Right? So what is that loss function? Okay, that loss function, remember, this is an unsupervised learning task. So the loss functions are going to be different potentially from what we saw for supervised learning. It's not just going to be clock entropy loss, for example, because there's not even labels. But you'll see that the loss will be actually interpretable. So first, there's loss is basically sum of two parts. The first part is what is called reconstruction loss. It's basically very similar to, hey, on training data, we want to minimize this loss to learn the parameters. Okay, but training data, I have this bunch of images. I don't have the labels. So what I'll do is try to reconstruct the image. Okay, so very similar to what we did in autoencoder. We'll start with an image and reconstruct that image, and therefore there's going to be reconstruction loss. Okay, how close is the new image, the generated image, to the input image. Okay, and there's also going to be something called latent loss. This loss is going to be, is related to the random variable z. Okay, this loss is related to the random variable z. So there is going to be an encoder in the variational autoencoder. It's very similar to the autoencoder architecture, and what we're going to do is minimize some sort of a minimize some sort of a difference between distributions. The difference or some sort of a difference between distributions. Okay. So, and that's the difference is captured using something called the KL divergence. It's just a measure of how different two distributions are. Okay, and that's what we're going to use to define the second part of this loss. Okay, so together, the reconstruction loss that we saw an example of in the autoencoder part. and the latent loss together. If we minimize these two losses, we'll get the parameters of the neural network. And with that neural network, we'll be able to do the sampling that we talked about, where we start with a random vector, pass it through this neural network, and we get an image at the end of the day. So here's a picture. Okay, so here's a picture of what's going on in the training. Okay, so we have an image. Okay, there's going to be two networks, an encoder network and a decoder network. And this is the network that we're going to use at test time. Okay, when we want to use that as a to generate new images, we're going to only use this guy. Okay, but while training, we'll also have an extra neural network, which is the encoder network. Okay. So we go from image to through the encoder to two vectors. Okay, I guess two vectors, two bunch of sets of numbers. One is the mean vector, one is the, I guess, standard deviation vector. Now you may say, hey, why is the standard deviation vector? Maybe it's a matrix. Even if it's a matrix, you can vectorize it, for example. So, or you can just think of, hey, my standard deviation, not standard deviation, but the covariance matrix is actually just diagonal. You can choose, make some assumptions so that it's still a vector. So what you do is, what we do while training, essentially, we'll start with an example image, encode it, get a mean encoded vector and a standard deviation vector for in the encoded space. And then from there, we can get a vector z. Okay, z is going to be now, a random sample with this mean and this variance. Okay, you can draw it from a normal distribution. Once you get the z, then you can pass it through again through a neural network, and you get an image. Okay, and what you want to do is tune the parameters of these two such that this image is very close to this image across your training data. Okay, that's what you want to do. That's how this is constructed. Very similar to autoencoder, but of course, this extra complication, which is the sampling. Okay, and there's also going to be some sampling here, which I think I'll show. I'll show in a second. So there's one sampling here, and there's going to be one more sampling here. But that's not super critical. But we'll add that if we'll add that later. So is this architecture clear? Any misunderstandings or anything to clarify at this point? Okay, so let's further, talk about this. So basically, there's a sampling step, but it turns out that even the sampling step, although there's a sampling step, while training, if you remember, there's going to be always a computational graph and a backprop operation. You can still backprop even though there's sampling. Okay, and that's not, let's not get into details of how that's done, but it is still possible to backprop. Okay, so that should not be an issue. So the whole thing of, hey, on the training data, let's reconstruct, but there's an intermediate sampling step here, is not a deal breaker. Okay. Uh, uh, yeah, I'll not comment on that. How the sampling is dealt with, because that's a second order point. The important point is the architecture and what is the loss? How is the loss function actually derived given this architecture? Okay, so yeah. Yeah. So as I said, if we are able to train this whole train the parameters here and here using training data, then you can actually allows for generalization, as in allows for sampling new images. And that's because you can ensure that you're not first of all, the sampling step is ensuring that you're not just remembering your training data. Okay, you're not just remembering this training data that you've inputted. Okay, this is actually, the sampling step is actually causing you to learn something more, some generalizing patterns in your training data than just each image individually, for example. So let's look at an output first and then go back to the architecture and the loss function. So here is an example from MNIST. Okay, so what we are showing here in this slide is just samples generated during training. Okay, so samples generated during training, and this is the original data. Original, and these are these reconstructed samples. Okay, these are the x hats at the far right from the previous diagram. So I'm passing some input. I think probably here the input is not shown, but it's some input, maybe 9, and I'm generating an output which looks like this, and eventually it looks like this. Maybe I'm passing 7 as input. I don't know, but these are just a collection of individual outcomes we just kept together just to show you that this is how generated samples look like. Okay, now each of these MNIST images, these are ideally not supposed to be in the training data. For MNIST images, it's kind of hard to, okay, you got this number 5. You can always go back to, hey, I have this 10,000 fives, which does this 5 correspond to any of my training data? You can always go back and check. For MNIST, it may look similar to some of your training data, but the idea is not to just remember your training data. Okay, so these are your generated numbers. So you can see that some of these are still confused. I mean, in fact, the first time this is early on in the process, and this is a little bit later. So early on in the process, you can see it's the variational encoder is completely confused of what to generate. Let's actually now come back to the model. So I just told you there's an encoder, decoder, and a sampling step in between. I also said that in between, the z is actually a random variable. Similarly, x is a random variable. So now we'll come back to justify why the loss function looks like that. Why the loss function should have a reconstruction component and a KL divergence component. Okay, and the reasoning is because of what we have is, as I said, a graphical model. And we want to learn the parameters of this graphical model, in particular the parameters of the conditional probabilities and marginal probabilities and so on. So we'll look at that in a little bit more detail now. Okay. So x, let's say, is an image, and z is a latent variable corresponding to an image. We already saw the graphical model. So, and in fact, I don't want to rewrite it. It's right here. So you have a z, and then you have an x. Okay. X is what is observed in training data. Eventually, what we want to use is training data, learn the parameters of this graphical model. Okay. We want to estimate. So what we want to estimate is p theta of z and p theta of x given z. Okay, x given z. So together, if you multiply these two, you get probability of x comma z, right? And that's a joint distribution over these two random variables. So we want to learn the parameter of this just joint distribution. Okay? But what we have is just the observations of the marginal distribution. So just the observations from the marginal distribution over x. We just have xi's, x1, x2, x3, maybe 100 images, 1,000 images. We just have one of these is seen, these is not seen, and we want to learn the parameters. Okay. So if we learn the parameters, then we can always generate, right? So we can always generate, hey, sample from z first. Okay, let's get a zi, and then given zi, we can get x given zi. Okay, if we know the parameters. Okay, if we know these two. Okay. And in particular, we're gonna define these, in a simple way. In fact, we're gonna further assume that this is a normal distribution. Okay. And this second guy is also a normal distribution with the mean and covariance being generated from a neural network. Okay. So those are the two, I guess, we'll keep adding extra, I guess, structure into the problem of what we want to be the distributions here. So that if it's a neural network, then it's the neural network parameters that we want to learn. Okay, theta star here is actually the neural network parameter that we want to learn. Okay? So this is like extra structure. So yeah. So as I said, we're going to assume a Gaussian distribution. We're going to assume the decoder is again neural network. Then what we want to do. So now this neural network has parameters, right? Weights and so on. Now what we want to do is learn the parameters by maximizing the likelihood of the data. So data likelihood is actually p of x, right? Some p of x is the data likelihood, right? Likelihood of seeing x. So we have seen x1, x2, x3, x100. Then we can get the log likelihood of the data, right? For example. So what we want to do is maximize the likelihood of the data. Now, what we'll do is We'll show how to maximize likelihood of the data next. But before that, I also want to add an auxiliary network into the picture. And that's the auxiliary network is an encoder network. Okay. So what do? I said, let's say I have input image X. Okay. So I want to say there is a neural network, or from image X, I can go to Z, and this is basically given X, I'm saying I can get a sample of Z. Okay. How do I do that? I can go from X to through a neural network, for example, get the mean and the covariance. If this mean and covariance is the mean and covariance of a normal distribution, then I can just sample. Like once I get the from X, I can get this and this, and from that I can get a sample Z. Okay, that's just normal distribution with that mean and the covariance. Similarly, from Z, I can, instead of estimating X directly, I can estimate the mean and covariance of X given Z and use that as parameters of a normal distribution to get an X. Okay, so I can do sampling. Okay, so I can do sampling to get from an X to a sample of Z, and given Z, I can get a sample of X. Okay, so this part is the decoder network, which we really care about, and this part is the encoder auxiliary network, which we'll use to learn the parameters of the, to learn the parameters of the decoder network. Okay. So with these two, now let me talk about the objective function. Okay, so the objective function is the extra strange term, which is I said that the objective function has two parts earlier. One is a reconstruction error, which is very similar to, hey, make x hat very close to x, where x is my training data, and x hat is something that got processed through this encoder decoder architecture. Now there's an extra term, which is the KL divergence term that I said. There's an extra term, and that extra term deals with this second random variable, this latent random variable, that random variable that we invented basically. So we want to justify that. Why is there an extra term, and how does it help? So for that, before discussing the last function itself, the last objective function, I'm going to tell you a little bit about KL divergence. So this is going to be a really short introduction to KL divergence. But the point is, for any random variable, let's think of a probability mass function. Okay, for any random variable, there is, folks in communications theory or information theory area have ascribed, what does it mean? Ascribed a notion of like a measure of information. Okay, so which means that if let's say an outcome, let's say tomorrow it's going to snow, it's an outcome of a random variable. If that outcome is very unlikely, okay, then there's a lot of information in that outcome. Okay, so that is captured by this measure. So if the probability of that outcome, probability of that random variable taking a specific value, okay, minus log of that is a measure of how much information is there in that outcome. So it's a definition, and it's actually intuitive, because if p of x is really small, then log of p of x is a really negative number. It's a really small negative number, a really, I guess, huge negative number. Okay, and minus log of that is going to be a hugely positive number. So there's a lot of information in this very unlikely event. Okay, and if let's say x is an outcome, which is like tomorrow it's not going to snow, then the probability of it not going snow, probability of not snowing, let's say it's pretty high, let's say 0.99, or maybe even 1 in the extreme case. Then if it's 1, for example, then the log of 1 is 0. Okay? And so there's no information. Tomorrow it's not gonna snow. Basically it's not a surprising thing. Okay, there's no information there. So intuitively, this negative log is basically trying to capture the amount of information in an outcome. Okay, and entropy is just an average of these information for each outcome. Okay, so a random variable has high entropy if it turns out that each outcome is surprising. Okay, each outcome is all the outcomes are somewhat surprising, then the random variable has high entropy. For example, a uniform random variable, okay, uniform random variable has high entropy compared to a random variable where one of the outcomes has 0.9 probability, the other outcome is 0.1 probability. Okay. And that's something that you might have seen when you're looking at decision trees, right? In decision trees, there's a notion of entropy a measure that you use to say how pure a node is, or if you divide a node into subnodes or subregions, then you can talk about purity of the node, right? So entropy or gene index, these are all measures of there are measures of some sort of purity, but here there's a link to that and this. But anyway, let's come back to entropy. Entropy is just a measure of information. Okay. And KL divergence is a measure of similarity between two probability distributions. Okay, measure of similarity or dissimilarity between two probability distributions. And its formula looks like this. Okay, it's a function, takes two distributions, probability mass functions, let's say, as input, and says, let me take the average of the log of the ratios of these two distributions. Okay, it's a KL divergence with respect to, let's say, the first distribution P. Okay, this is defined as a KL divergence. So this is somewhat similar, but not the same, as you can think of, hey, how much entropy is there? P of x log P of x minus sum of P of x log P of x, right? So this is, this is actually equal here, which is also equal to some sort of a, this is equal to entropy of Q, smallest q, minus entropy of P. So KL divergence is some sort of, it's not equal, sorry, here it's somewhat similar, because this is actually not entropy of Q here. This is not entropy of Q, but KL divergence is some sort of, hey, how much information is contained in P which is not contained in Q. Okay, that's the informal interpretation that we want to use. But for us, for today's session, we're just going to use this formula. Okay, it's just some sort of for internship, they only for us, we just look at the formula and also a couple of properties that follow. The property is KL divergence is always positive, so always non-negative. Okay, if you pass the same distributions, there's no divergence between those two distributions, so that's the lowest you can get. So if two distributions are the same, KL divergence is 0. The moment two distributions are different, KL divergence is always a positive number. Okay, that's the first property. And second property that we don't need is this is not the KL divergence is not symmetric. So the KL of a Q parallel Q comma P is not the same as a P parallel Q, but it's not. This is the second property. It's not symmetric. But anyway, this is the definition of KL divergence, and we'll see that in the loss function of variational autoencoder, we're going to use. It turns out the loss function is going to involve this KL divergence. Okay, but how do we get the loss function? Okay, there's a very principled way with which we're going to get the loss function, which is we're going to start with the idea. Hey, we have data. We want to maximize the log likelihood of the data. Okay, we start with that point, and then using a sequence of algebraic manipulations, we'll see that we'll get to a objective which involves a reconstruction error and the KL divergence. Okay, so remember, we are always, since we have a graphical model, which means that we have a joint distribution between x and z, we'll start with a very logical principled approach, which is to maximize, find the parameters that maximize the likelihood of the data. Okay, likelihood of the data. We start with log p of x, something like that, and then we get to a objective function which turns out to be like some sort of reconstruction error plus a KL divergence. Okay. Any questions here? Okay, let me spend the next couple of minutes talking about this, defining this objective function, because and you'll see that this exercise is not so important to remember all these steps, but to see that there's a very principled way in which we got this loss function. Okay, very similar to and this is the way you derive loss functions when you have such graphical models. Even for LDA, latent digital allocation, there's a loss function. We did not see the loss function when we talked about LDA, but that's also derived in a very similar way. Okay, so since we did not see the loss function for while saying, hey, how do we train an LDA model? We are going to see one example here. Okay, so let's start with the log likelihood of the data. Okay, so p theta of x, xi, I represents the ith example. P theta of xi is the likelihood of that data point xi. Theta is the parameter that we want to learn. Okay, so this theta is basically the decoder network parameter as well as the encoder network parameter if it's relevant. Okay, and we'll see that it is relevant. So log of the likelihood. Okay, this is what we want to maximize. Now log of likelihood. Let's take an expectation over z random variable. Okay, this log of likelihood it just depends on the parameters theta and the example xi. Let's take an expectation with respect to z. Okay, this expectation, expectation with respect to z, where z is determined according to this conditional probability. Okay, conditional probability of q phi of z given xi. So what is q phi? Remember, this is the encoder network with the extra normal distribution. So it's producing the mean and the covariance, and then you draw a sample. So we take an expectation with respect to z, but z is not. You can see that this internal thing has nothing to do with z. Okay, there's no z parameter, z random variable in there. It's a constant with respect to z, any value of z. So we can always do this expectation operation. So this is equality. Okay, it's like saying, hey, what's the expectation of one? It's just one is like saying one is equal expectation with respect to a random variable z, which is normal with mean 0, 1 of 1. Okay, this is true, right? So when we do this, and then what we do is use Bayes rule. Okay, so p theta of p of x, remember, is p of x given z times p of z, okay, divided by p of z given x. Okay, this is just Bayes rule. Okay, what did I do? And it's next exactly the Bayes rule form. If I exchange these two, it's exactly Bayes rule. Right? So this is Bayes rule step. And then what we do is multiply and divide by the same term. Okay, multiply and divide by a constant, a fixed thing. There's no change in the expression, right? So we just multiply and divide by the same thing, which is again qp of z given xi. Okay. Okay, we did the multiplication. Then what we do is now use the property of log. Okay, so log of many such terms. So log of all these terms. Okay, we'll use the property that log of a times b divided by c is equal to log of a plus log of b minus log of c. Okay, this is the property we can use. So what we're going to do is split terms. Okay, so first we're going to pick up only this term. Okay, that's here, and then we'll pick up terms this guy and this guy. Okay. This guy and this guy, these two, the ones in the stars as the second term, and the third term is these two tick marked. Okay, so this one and this one. Okay, that's this term. So we are just doing some algebraic manipulation to split it into three terms. Okay, that's what we did using this that we know, this property that we know. Okay, and we are pretty much there. What we do is now interpret each of these terms. Okay, and in fact also drop one of the terms. So let's do that next part. So interpreting the term implies this term, the second term, turns out to be it's a KL divergence. Okay, you can actually see that because it's the expectation of z of something with involves z and expectation of z also is with respect to this, right? So that's just a negative KL divergence. Okay, so that's why, sorry, that's just the KL divergence. I'm sorry about that. So that's just KL divergence. Similarly, the last term is also KL divergence. Okay, it's a KL divergence by definition. Okay, so now we have these three terms in the expression. So it's all equality. So we started with, hey, what is the log of my likelihood of my data point xi? Okay, that likelihood of your data point xi in this model where there's extra latent variable z involves three terms. Term 1, term 2, and term 3. Okay. Now what we'll do is what we want to do is maximize the likelihood of my data. Okay. Now instead of maximizing the likelihood of the data, which it turns out it's hard. Okay, and that's why we are doing all this extra algebraic manipulation. We can actually maximize just two of these terms. Okay, so firstly, remember that this, as I said, KL is always greater than or equal to 0. So what we can do is drop this last term. Okay, we'll just drop it. Okay, that means that the left hand, that means that if we drop a positive term, then of course the right hand side is going to be smaller than left hand side. Okay, So let's just drop this. Okay. And let's call this the objective. Okay, so instead of maximizing this term, we're going to maximize just terms 1 and 2. Okay, and terms 1 and 2, are let's call this script L for the loss function. Let's call it the loss function. And that's what we're going to maximize. So we're going to maximize the first term and the second term. If you can see, the second term is the KL divergence between, is the KL divergence related to the random variable z. And the first term is actually the reconstruction error. Turns out it's related to the reconstruction error. Okay? It's the yeah, it's related to constructing x given z, right? So that's the reconstruction. Given x given z, tell me what x is. That's reconstruction, right? So and we can actually see that remember, if we substitute back the normal distribution expression, turns out that the first term actually looks like some sort of x hat minus x type of a term. Okay? Very similar to what autoencoder expression. Okay, because of normality and all that. The second term is just the KL divergence with respect to the latent random variable z. Okay, so that's how we end up with this loss function. Okay, this loss function for variational autoencoder. And the loss function involves the parameters theta and z. Theta for the decoder network, phi for the encoder network. Once you have this well-defined loss function, you can just apply the same ideas that you've seen for for all your PyTorch-based experiment assignments that you've worked on, right? So you can define this is a custom loss function, and you have the two networks p theta and q phi, and you can those are just extensions of nn.module, right? And you can just do backprop to learn these two parameters, okay, or over your training data, and that's this objective here. So just to summarize, so I wanted to spend a couple of minutes on that loss function definition only because you haven't seen maximum likelihood estimation in general in this course, but I hope you have seen it elsewhere. But we started with the objective of maximizing likelihood of the data, and in a principled way got to a proxy objective, which involves the reconstruction error plus a KL divergence term. Okay, and this is how you will see many of the graphical models parameters are learned. Okay, they have a similar procedure. And that's why I wanted to show an example. Now let's come back to VAE's architecture. Okay, so VAE's architecture, if you really think of what's going on, is you got an input for every input image. Let's say in training, you go from input image through the neural network, get two vectors, okay, and you just can concatenate them, or just you get one vector and just interpret the first part to be mean and the second part to be parameters of the covariance matrix. From there, you get a sample with a normal distribution with this mean and covariance. From that sample, again, go through a neural network, produce a mean and a covariance. Okay, use those two to produce a final sample. And this final sample is actually an image. Okay, this input also is an image. Okay. In between is a random variable z. So you don't really care about the value of the random variable, but the distribution over this random variable. Okay. And in terms of the whole architecture, there's a convolutional operation going on up to getting a latent random variable, and from latent random variable, like a realization of the random variable to the image, there's a deconvolutional or transpose convolutional step going on to get back to an image. Okay? During training, that's what you do. While doing sample generation, you only care about the thing that I highlighted in the box, okay? Which is this. So you start from a normal distribution. You start from a normal distribution, sample a z value, pass it through the decoder network, get the mean and the covariance, and use them as parameters in a normal distribution and get an image. Okay, that's how you get an image. Okay. And this, I guess, this was from a few years ago. So, and you can see some images here actually. Let's not focus on the whole slide. Let's just focus on here. These are images. I mean, these are, I mean, it may look like they are just minor transformations, deterministic transformations of input images, but that's not the case. These are actually, it goes through that process, and these images are not there in training data, but also are not exactly the same as training data. Okay, they're not just perturbed versions of the training data, for example. Well, you can do that for even CFAR10. You will see that the images are not completely correct. So you can see, for example, there is random stuff on the side, not well-formed images, but but I think there are many variations these days, and some of them are pretty realistic looking. Any questions here at this point? Not. Let's take a break. Let's resume at 8:02. 8:02. Okay, so welcome back. What I want to do now is give you a few examples and pointers, and there are some links on the course lecture details page. I encourage you to look at it after class, but I wanted to show you a couple of things in the meantime. Um, so I don't know how many of you have heard of this website, and there are actually many variations of this. This is called thisperson.notexist.com. So actually, every time you refresh this, you get a face, and this face is actually not from some training data. Okay, so not from some realistic, not from some true images. Okay, so you can see that it's actually imagined by a GAN, and you can look at the description of how this is generated. Okay, and we're going to discuss GANs, pretty soon. Let me actually see where the chat window is. Okay. Okay. So let me just paste the link. So this is a very fun website to explore, and you can also look at the links below on what a GAN is and some code bases that are related to it. So this is one example. The second thing is an example called visualizing and understanding generative adversarial networks. So it's something that you can play um, where what you can do is basically the point here is that these are generative models, right? We saw VAE for quite a bit, but GANs also, they generate images, and you can actually do extra bells and whistles. Basically, for example, you can see in this image, if you remove domes, removes a dome here, and add domes, adds extra domes here. Similarly, add trees, adds trees here. So these are generative. These are not real images, right? So I mean, in the sense that now when I add trees, there's not a photographed image. Okay, this is something that was generated from a neural network. Similarly, if you add doors here, you can see how those are being added. So this project is just trying to understand how GANs work, but uh, you know again, another link to try out. And I guess the more I guess good starting point is actually the PyTorch examples or PyTorch tutorials. So there's actually a tutorial on GANs. So we're going to talk about GANs in a second, but at the end of the day, as I said, it's basically a way to generate new images. So you can see here, it's using this data set of celebrity images to uh, to generate new images. And I don't know if they have a snapshot of the new images. Yeah, so these are new images. You can see that they're not that well formed, many of these images, but you can, and this is linked on the course web page, by the way, the lecture details page. So you can look at this, you can figure out, you can actually do this in maybe Collab and try out how to generate new images. Okay, so paste this link as well. So these three are related to GANs that we're going to look at next. But just to complete the story about VAE also there's a code base in PyTorch. In fact, it's on the PyTorch's repository on GitHub. So it's also worth looking at that code base. So here it just shows how to just run it. Like you can look at the main and you can look at the results. Actually, like there's no results. You can look at the main file to see how they have encoded this variational autoencoder. Okay. I hope these links, I mean, so this the last one is about VAEs and the other ones are about GANs. I actually also had some videos related to GANs, but in the interest of time, I'm gonna directly jump over to discussing GANs. Any questions here? Yeah, I guess please feel free to ask questions because this is a relatively new topic, and unsupervised learning is something that we've not seen before, at least in this course. So do ask questions. So okay, let's move forward with the next object. Okay, so remember we are trying to create an object from which we start with a random sort, like something like a z, normally distributed. Start with some vector z. At the end of the day, we want to get an image. Okay, so we want to get an image, and hopefully this image is not one of the training examples and not slightly perturbed version of the training example, but something which is from the distribution of images. So it's even hard to imagine what is the distribution of natural images that have been photographed by very different people. So, but we want to get something like that. Okay, that's the aim of both VAE as well as GANs, and we'll look at GANs now. And most important feature for each of them is how their loss function is defined. How the architecture, by the way, is going to be very similar to a CNN or the opposite of a CNN, going from a vector to an image, which we briefly discussed. So the neural network parts are going to be just pretty standard. Okay, so you can have 4 or 5 layer convolution layer for the encoder part, and maybe a decoder, which is just the opposite of that, inverse of that, on the decoder part. Okay, for VAEs, for example. What's interesting is how the loss function and the training is defined. Okay, so for VAEs, we saw how the loss function is defined. We also saw how an image is first transformed to a mean and covariance, and then from that we get a sample. And that sample is passed down to the decoder and then is reconstructed. And then we have a specialized loss function that lets us train the parameters of the network involved. Right? For VAE, that's what we saw. We're going to do something similar with GANs as well. Okay, so the idea is, and this is where the implicit versus explicit contrast comes in. So VAEs, we actually had a joint distribution between two explicit random variables, X and Z. And there were explicit conditional probabilities, of course, through neural networks that were expressed there. So in fact, we were trying to fit the parameters of an explicit joint distribution between X and a latent extra latent random variable Z. Okay? Whereas here, there is no such notion of random variable probability distribution and all that. Okay, so that's where this notion of a implicit density function comes in. And in fact, GANs take a very interesting approach called the adversarial or the game theoretic approach. Okay, so we'll see how the approach makes sense. So what GANs do is there's going to be essentially two scenarios, and also involves two players in some sense, two players. Okay, so it's a game. So games generally have players. So it's going to be two players. Okay, so the first player, let's call it P of X or a discriminator. What it does is, so let's talk about the first scenario. In the first scenario, let's say there's a real image. Okay, a real image. Okay, a real image is something that's there in the training data. For that image, this discriminator is this player who wants to score this image as, hey, this is +1. Okay, he wants to produce a score +1 for this real image. Okay. Whereas the same player, they want to produce a score 0 for a non-real image. So let's say there is a image sample from a model, okay, some generative model. Then that image, is given to this discriminator player, and the player wants to make that value produce a score which is close to 0. Okay, that's their objective. Produce a score 1 for a real image, produce a score 0 for a non-real image. And it's basically, and you can imagine this can be accomplished by a binary classifier. Okay, with images as input, a score as an output, you can literally do a CNN with 2 classes, right? Now there's another player, which is the generator player or the G player. Okay, that player, it's gonna start with a noise, a random vector. Okay, start with a random vector and produce a sample, produce an image. Okay, so start from a random vector, produce an image. Okay? And of course, you can imagine there's parameters here. This network also has parameters here. Maybe something else. And the second player wants to produce images such that the discriminator produces score 1 for these images. The generator wants to produce these synthetic images or non-real images such that, and it wants to tune its parameters such that when this synthetic image is passed through the discriminator is going to confuse it with real images and score it high instead of scoring it low. Okay? So These two players are in contrast with each other, right? They're against each other. Discriminator wants to discriminate between real and non-real images. Generator wants to make images such that they can fool the discriminator. They they're trying to make the discriminator lose, not be able to classify the non-real ones as non-real. Okay. So that's the idea. And here's a simple, I guess, illustrative example. Okay, before we're talking about images, let's talk about simple one-dimensional variable. Okay, let's say x. Let's say there's a generator, okay, with some parameters theta g, which is starting from some random source produces a random variable x. Okay, starting from some random source in the sense that starting from some random variable. Okay, b. Okay, let's say b is also a normal distribution, for example. So you're going to g is a function which goes from, hey, give me a random z. From there, I'll give you an x. Okay, that's what it does. So for every z value you sample, you can get an x. Let's say that guy is the green curve here. So in this picture, let's say the green curve is the one produced by the generator. Okay. Now, let's say this dotted curve here in this figure is a true data. Okay, so true data is this dotted curve, and the green one is produced by the generator. Okay, so here I've shown it as like two separate peaks, but you can in this picture you can see that they're very somewhat close to each other. Okay, now if there was two separate peaks like this, okay, one is produced by the model, okay, by the generator, one is the real data. You can imagine a discriminator which sees data like this, right? So this is x, right? Data like this can easily create a classifier, right? A classifier is going to be this. Okay? On the left side, classify everything as 1. On the right side, classify everything as 0. That's a good classifier because it's able to discriminate between the generated samples and the real sample. But imagine if the green curve is closer and closer to the dotted real data. Okay? And that's what's happening in this picture. The green curve is closer and closer to the dotted region. In the more it gets closer and closer, the more the discriminator is not able to discriminate between the data and the synthetic data. Okay, and that's what we want to do. So change the generator such that it gets closer and closer to the real data pattern, so the discriminator is fooled. Okay, so that's the intuition behind setting up an objective function and the training flow for GANs. Okay, um, any questions here? Okay, let's actually revisit this idea again. As I said, generator is trying to fool the discriminator, as in like make the discriminator give a score of 1 when it's supposed to give a score of 0 for synthetic images. And the discriminator network or the discriminator is trying to distinguish between real and fake. Real, it wants to produce a score of 1. Fake images or non-real images, it try to produce a score of 0. That's what we want. So real images are basically from the training data, and these synthetic images are from starting from a random noise, passing through a neural network, and you get an image. And we know how to do this. We've seen this transformation before. Um, so let's now look at the training process. Okay, so the training process, and that's where I guess the differentiation comes. It's a very different loss function and a very different training process. Unlike maximizing data likelihood and in the VAE case. So let's say we have a random variable z, okay, and it's a latent random variable. From z, if you pass it through this function neural network generator, then you get a sample, which is g of z, sample of an image. Okay, so this is an image. Okay, now if you pass this image to the discriminator, it should ideally say it's not it's not a real image. Okay, and that you can compare, that you can define, that you can you know evaluate score and how well the discriminator is doing by defining an appropriate loss function. Okay. Similarly, if from a real world data set, okay, this is like a data set representation, you get a sample X and passes to the discriminator, hopefully it says it is real. Okay, it is, produces a score of 1. And if it doesn't produce a score of 1, again, losses has to take care of it. So the loss influences training this two-class classifier, the discriminator. The loss also influences training this generator. It's going to be almost the same loss. Okay. So in particular, let's write the loss function. The as I said, the generator and discriminator are kind of opposing each other. Okay, the discriminator wants to discriminate the generator from the real data, whatever generated data from real data. And generator wants to create data which is as close to real, therefore fool the discriminator. So it's they're opposing, right? So here is an example loss function. So on the real data, you want to minimize the negative cross entropy. Okay, so you want to minimize the negative log likelihood or maximize the log likelihood. Remember in VAE case, we said maximize the data likelihood. It's exactly the opposite of that. It's exactly the negative of that. So it's like minimize the data likelihood, real data likelihood. Okay, that's this function here. And at the same time, this discriminator should also minimize the negative or maximize the generated data's likelihood of being 0. Okay, so in the sense that 1 minus d is if d is low, then 1 minus of d is going to be high. So this is the second term basically is the likelihood of you predict is the likelihood of the generated data. Okay, so you want to set the parameters of d such that you minimize such that you minimize the loss the loss associated with the likelihood of the generated data. Okay. So remember with minus, this is clear. This is just the negative log likelihood of the real data. But this extra minus sign, okay, this is the likelihood of the likelihood of the discriminator predicting a 0 for this negative for this generated data. Okay. The more you produce zeros, the lower the loss will be. The more you produce closer to 1, the higher this loss will be. Okay. And what is the loss function for the generator? Loss function for the generator is exactly the opposite. Okay, it's going to be just minus of this above loss function. Okay, now you may say, hey, where is the generator coming into the picture? It's coming into the picture here. So this x here is produced from the model. So it's actually produced from the generator. This x here is just the training data. It's just the average of the training data. Okay. So let's get the optimal strategy. Let's now look at, because it's not super important. Let's now talk about, what we've done so far is say we've intuited that, hey, discriminator is trying to, discriminator is getting scored against this loss function, which is trying to maximize the likelihood of the real data and minimize and maximize the probability that the discriminator predicts a 0 for the non-real data. Okay, that's the second term. Okay. And the objective function for the generator is just the opposite of that. Okay, so generator is trying to set its parameters to reduce an objective, and the discriminator is trying to the discriminator is trying to set its parameters so as to reduce its loss function, and the generator is trying to set its parameters so as to maximize this loss function. Okay, if you interpret it that way. And we know now we have the objective functions for the two networks. Okay, now we're going to train these two networks in tandem. Okay, so we have this loss function for this discriminator that needs to be minimized. So we'll change the parameters of the discriminator to minimize that objective. Similarly, for the generator network, we have a objective which needs to be maximized. So we'll change the parameters of the generator to maximize this objective. Actually, it turns out in the next slide, I actually do the opposite, which is to just make the loss functions as scoring functions. And so therefore, for discriminator, I'm going to do a maximization, and for generator, I'm going to do a minimization. But it's the same idea, whether you just need to do for one set of parameters a maximization, for another set of parameters a minimization. Okay, so that clears it. So how do we actually do this? As I said, we need to do this in tandem. So what do I mean by that? We first create a mini batch of the real data and create a mini batch of generated data. Okay, we generate data given current parameter. Okay, current parameters have something. So I pass z, I sample a bunch of z's, pass it to the generator, I'll get a bunch of images. Okay. Those images have nothing to do, may be very different from these images in the sense that, if let's say the real data is an image of a woman, this generated data doesn't have to be an image of a woman. Okay, there's no relation, 1:1 relation. It's just that we have a bunch of real data and non-real data. It's just that the generator has to somehow score high on the real data and score low on the non-real data. So let's say we created these two mini batches. Then given these two mini batches, our objective function is completely defined. Okay, for those mini batches, the objective function is completely defined as a function of the generators, as a function of the discriminators parameters. Okay? Let's not worry about generators parameters. Okay, at this point. So we have the discriminators current candidate parameters. They are scored, right? So there's some loss value that you accrue. Okay? We'll backprop to update the parameters. And as I said, we want to, in the next slide, as you'll see, we want to maximize the reward function or the negative log function, negative loss function. So we'll do a gradient descent. Okay, gradient descent for this guy. And similarly, once we've done that, we've freeze that the discriminator completely, as in we're not changing the parameters. Now we have now what we can do is change the parameters of generator. Now the discriminator is fixed. Now we change the parameters of generator so that the discriminator produces high scores for the synthetic images. Okay, so that is achieved by minimizing the appropriate scoring, scoring function. So here we'll do gradient descent. So just as a contrast here, so this is the loss. So what I'm trying to say is that for the discriminator, we'll just do minus j of t, maximize minus j of t for the discriminator. Actually, for the generator, we'll do minimize j of t. Because minimizing j of t is the same as maximizing this. Yeah, let me come back to, let me show this actually explicitly here. So the same j of t expression, now negative j of t expression is written here. So you'll see that if you compare 2 slides ago, the only thing missing is the negative signs. And that's why I said maximize over the discriminator parameters and minimize over the generator parameters. Okay? These are the two steps we want to do. So we want to do gradient descent with respect to theta d and gradient descent with respect to theta g. Okay, so therefore, same backdrop idea. It's just a gradient descent is slightly different from gradient descent, and we know what the difference is. So we just need to do that. We want to alternate between gradient descent and gradient descent of these two different parameter sets, and that's pretty much the training procedure. Okay, just to again recap. This is the likelihood of the data. Okay, this is literally the likelihood of the data. So you're maximizing the likelihood of the data with respect to these parameters theta d. So you're changing the different parameters to maximize the likelihood of the real data. Okay. This is the log probability of the discriminator producing a low score for the synthetic data. Okay. So you are trying to produce low scores, and therefore 1 minus that is high scores for synthetic data. And again, that's why you're maximizing with respect to theta d. If there was no 1 minus, then generally there would be minus in the front example. Okay, so I just explained the training procedure again. Recap. So you freeze the generator parameters, for example, and use the loss function to first update the discriminator parameters theta d, for example, using gradient ascent, and freeze the parameters of the discriminator and use the loss function to update the parameters of the generator using gradient descent. Okay. And that's about it. And the generator architecture, we have seen this before in VAE as well. Going from a vector to an image is not an issue. You just have to apply a sequence of transpose convolutional operations, or I guess informally called decon operations. And this is exactly the code that I showed earlier, and which is in the PyTorch repository. So you should explore that later. Okay. So, and I already showed you some images for GANs, so I will not spend too much time here. This is actually pictures of bedrooms or rooms in the this data set. So, and this is just an exploration of, hey, once I have trained this GAN, I can take just the generator part, forget about the discriminator, just the generator part, and that's exactly what we want. It's going from a Z vector. Okay, I put it through the generator part. It's producing me an image, right? So it's giving me an image. So this is actually just a screenshot of that. I mean, this is just a sequence of those images. When I slowly vary z from, let's say, z1 to z10, I'm getting this sequence of images. Okay, so that's roughly the idea here. Um, yeah, you can also do extra things like you can get the um, embedding. So you can get the you can get Z1 for somebody with a glass. You can get Z2 with somebody without a glasses. Z3 for a woman. And then you can do you can do an arithmetic and see if you can generate with these whatever the output comes. Maybe it's it turns out sometimes you can get these types of byproducts, and we've seen this for Word2Vec as well. But I would say play around with the examples in the links that I just shared. For example, this person does not exist, or GAN dissect project that was recently published. So you can get a feel for what is GAN doing in the latent space. So let's not worry about this. Yeah. Any questions at this point? I think we're almost at the end of this lecture. I want to spend a moment on just a pictorial representation of what's the difference between VAE and GAN, and just to close up this chapter. So both VAE and GAN are way to generate new images. Okay, they are basically trying to do a really hard problem, solve a really hard problem. It's like if you think of natural images, even if you have a million images, from those they're trying to get a distribution over these natural images. Okay, once you have a distribution, you can always sample from them, right? Like getting a normal distribution from a bunch of scale, numbers, scalar data points, and then getting samples, new samples from that normal distribution. Very similar idea, but with images. Okay, and that's what is super hard here. For GANs, uh, for VAEs, as you know, there is a reconstruction. So while training, you're just directly using training data to try to reconstruct it. At the same time, there's an intermediate sampling step involved, and you're also trying to minimize some sort of a KL divergence distance between some normal distribution that we want to have for this random variable and what the encoder is doing. Encoder is going from some arbitrary crazy distribution to some distribution over Z, which is as close to a normal distribution as possible. That's what the second term, the loss function, is doing. Okay. Um, there is a VAs are well founded in the sense that they are basically a graphical model, and so you can interpret the probability of probability of the images and so on. But it turns out the VAs, are at least the vanilla version that we saw in this today's lecture, is not the best in the sense that it gives you roughly somewhat blurry images. And the source for that is because we are assuming some Gaussian distribution assumptions in quite a few steps, okay? Both on the output, like especially in the KL divergence term, that term is easy only if you assume Gaussian distributions pretty much everywhere in this model. Um, and GANs, we do get sharp images. Remember the training process is very different. It's basically a generator trying to play against a discriminator, there's two sets of neural networks being trained. There is no probabilistic interpretation as such. There is no explicit probability distribution, and that's what we said as an implicit distribution, implicit sampling object here. And and there's extra points like how do you get given an image, can you get um, get its latent representation? It's not easy for GAN, and whereas for VAE it's easy because you can just pass the image through the encoder, you can get the latent representation. Okay, so those are the key differences, and a few more differences are listed in the both slides, but I'll stop it here. If you have any questions, stay back and ask, and if not, have a good rest of the evening. Thank you.
Professor,